Everyone, I'm Cassie Sands. I'm a PhD candidate at the University of Arkansas, and I'll be presenting to you today about ARKSAT 1, one new CubeSat developed at the University of Arkansas. So just a quick overview, here's a rendering of our satellite. It's the one new CubeSat. We're scheduled to launch in early 2021. We were originally manifested on SpaceX 21, set to launch out of Cape Canaveral in October of 2020. We had some COVID-related delays, but we're just a few months behind at this point. So we have two primary payloads. We have a high-power LED, which will be tracked from our ground station. We're also testing the solid-state inflatable balloon deorbiting system. I'll refer to it as SSIB from now on. This is applicable to small satellites, not just CubeSats, so anything 180 kilograms or less. It consists of a PCB solid-state gas generator chip, a space-compatible balloon film structure, and an integration subsystem for modularity. So just to provide some context, so ARKSAT 1 is our initial satellite. Using the ISS as a launch platform, we were selected for launch under NASA's 8th CubeSat launch initiative. Its initial flight demonstration for UA CubeSat. We're also the first student satellite in the state. It'll also be space environment testing of the SSIB, as well as some atmospheric measurements between our satellite and our ground station. And then building on that is ARKSAT 2, which is a 2U CubeSat, which will have some chasing and tracking demonstration, as well as a CubeSat propulsion system used for attitude control. We're expected to launch late 2021, early 2022, so about a year behind ARKSAT 1. And these are the first two steps in developing what we call the DOS-Cube system, which is separate spacecraft, separate CubeSats or small sats, one with an emitter, one with a receiver that can track each other and perform planetary atmospheric measurements. So here's an exploded view of our satellite. You can see our center frame, our top and bottom frame. Here's our plus Z face, minus Z face. Our minus Z face is planned to be pointed at the Earth that's like our nominal operational mode. And that was just to match the nomenclature of our integrator and their deployer. The SSIB is over here on the plus Z face. Here's what it looks like open and closed. We have solar cells on all 6 faces. We have dedicated boards for most of our subsystems. So we have our primary EPS, our radio, onboard computer, secondary EPS, as well as an image processor board. Our LEDs over here with a condenser lens on the minus Z face. We also have a series of optical and infrared sensors. We have magnetorquers, so we have printed coils and PCBs for attitude control. Yep, I think that's everything here. So we're using gallium arsenide solar cells on all 6 faces. Our primary EPS is a Clyde Space 3G with integrated 20 watt-hour batteries, and those are powered by our solar cells. We have an additional bank of 10 100 milliamp hour LiPo batteries that were developed at our university that we wanted to test in space. And the secondary EPS is driven by the primary EPS, and it controls the LED, which is 36 volts nominal. The LED is a luminous CXM 27 Gen 1 white LED. It's 11 to 12,000 lumens. It has a 50 millimeter condenser lens on the minus Z face. The LED has an apparent magnitude of about 3 at our orbital altitude. And the thermal requirements limit us a little bit. We can only operate the LED for about 10 seconds. We do have heat pipes used to dissipate some of the generated heat to the aluminum side frames, but thermal control in space with little or no convection is a little tricky. So we have, as I mentioned, we have optical and infrared sensors. These are primarily used as input to our attitude determination and control system. We're also doing image collection and downlink. 5 of our faces, so all but the minus Z face, have a low resolution infrared sensor, an AMG 88. And then the minus Z face has 4 infrared sensors set up at a 60-degree angle so that we can see the entire hemisphere of the Earth from our orbital altitude. On the minus Z face, we also have 2 high-resolution Melexis infrared sensors for more accurate pointing, as well as 2 optical cameras for daytime ground tracking. Each face has a TDK 9-axis MEMS gyro accelerometer and compass. We do have a printed magnetorquer on all of our faces as well. Our nominal operational mode is nadir pointing, but we also plan to have a finer pointing mode to point the spacecraft to our ground station. We have 2 radios on ARKSAT 1. So our primary radio is an AstroDev Lithium-1. It's half duplex, operating at 435.45 megahertz. We also have an experimental LoRa radio at 906.3 megahertz to be used for uplink only. So the Lithium-1 has been tested in space before. It has flight heritage. The LoRa, as far as we know, has not been tested in space at all. And we believe that it can do We believe that it can do what we need a radio to do, but it's a lot cheaper than the Lithium-1. And so we're kind of testing it and seeing how it works, if it has any issues. We have 2 tape measure dipole antennas that'll be deployed with nichrome burn wires after we're deployed. We have an amateur radio club and station on campus, and we're sort of building on that. We're building our ground station into that existing infrastructure. And we'll host the identical Lithium-1 radio to that aboard our spacecraft. And on the roof of that same building, we have an elliptically polarized Yagi antenna. So all of our structures was machined in our student machine shop through our mechanical engineering department. So our center, top, bottom frame, as well as the LED, lens cap, and housing. The center frame is machined from a 4x4 inch square aluminum 6061 stock extrusion with 1/8 inch thick sidewalls, and the ends, the plus and minus Z face, are milled from aluminum 6061 solid billets. That's based on the NASA Ames CubeSat design. So over here you can see one of our undergrads early this year machining a center frame prototype. There's a red plastic piece in here, and that's used to prevent warping during the machining process. So our SSIB system. So most CubeSats operate in low Earth orbit at around 300 to 550 kilometers. And at those altitudes, aerodynamic drag is the dominant force. So the SSIB utilizes this force to reduce the orbital lifetime of the spacecraft. It's essentially a balloon that inflates in space and increases your cross-section. So it's applicable to small sats 180 kilograms or less, and it'll help us meet FAA requirements to deorbit within 25 years. So on the bottom left here, we have a MEMS prototype of the SSIB. We're actually going to be using a little bit of a simpler PCB version on ARKSAT 1, but the fundamentals are the same. And over here we have a rendering of the SSIB module, as well as a 37 centimeter inflated balloon. So the SSIB consists of a solid-state gas generator chip with a 2D array of sodium azide. That would be this right here. This is an 8x8 array. We've also tested 2x2 arrays, so you can size it differently based on how big your spacecraft is and how big of a balloon you want to inflate. So these wells are filled with sodium azide, which is a solid, but then when the system is activated, it heats up the wells to greater than 350 degrees Celsius, and it decomposes the sodium azide, releasing nitrogen gas. And it uses about 1 watt of power for about 10 seconds, and gas is released within milliseconds. It's modular. It's designed to fit within CubeSat requirements, so it's 10 by 10 by 2 centimeters. The wells are coated with 15 micron thick Parylene coating. Sodium azide is slightly toxic. It's also somewhat shock sensitive. The toxicity is well below toxic thresholds. We also performed shock testing, and there was no dislodging of the material. We have done vacuum chamber inflation as well. So we inflated a 10 centimeter mylar balloon here on campus at 5 millitorr. So here's a graph showing how much the SSIB would decrease your orbital lifetime. So this is done using AGI STK. So this red line here is 0.01 meters squared cross-sectional area. That's just nominal for 1U CubeSat. This 0.1 meters squared is with a 37 centimeter balloon inflated. So we assumed a 1U CubeSat, 1.33 kilograms, 28.5 degree orbital inclination. And based on these results, a 37 centimeter diameter balloon would significantly reduce the orbital lifetime. So with a 700 kilometer initial orbit, it would reduce from 40 years to less than 5 years. 550 kilometer initial orbit, it would decrease from about 2 years to less than 1 year. So our ground tracking system, so as I mentioned, there's a separate emitter, in this case our satellite, as well as a ground tracker. The ground tracker hosts a spectrometer. We're using an Ocean Optics USB 4000 UV vis NIR. It operates from about 350 to 1050 nanometers. So over here on our right, this is a rifle scope and our frame and tripod and fiber optics. There's a camera in here as well. Our first prototype doesn't include the motors for azimuth and elevation control, but those will be incorporated at a later time. And this prototype was initially tested in June of 2019, and we collected Luna spectra with an integration time of about 1 second. So here's a picture of the moon as well as the spectra that we collected, and you can see these nice absorption bands here, just as we expected. And those can be evaluated using a spectroscopic database such as HITRAN. And there are future efforts to miniaturize this and apply it to a satellite system. So ARKSAT 2 is a 2U CubeSat. It's built on ARKSAT 1 infrastructure. The center portion is basically all the same electronic stack from ARKSAT 1, and the remaining half a U on each side is dedicated to attitude control propulsion system. We're expected to launch in late 2021, early 2022, so about a year behind ARKSAT 1. The propulsion system is low-cost, biocompatible, non-toxic, non-flammable, non-pressurized. It uses water with some propylene glycol as a propellant, produces millinewton levels of thrust. It's applicable to nanosats, so 1 to 10 kilograms. Produces about 100 seconds of ISP. Depending on your satellite mass, that corresponds to a delta V of about 114 meters per second. There's 4 10 millinewton nozzles providing 4 degrees of freedom for thrust. For maneuvers less than 60 seconds, no heating is required, but there is a 10-watt integrated heater for longer maneuvers if needed to overcome the heat loss to vaporization. And so the DasCube system is intended to complement existing planetary atmospheric measurements. So a multi-satellite system with a separate emitter receiver could remove a lot of the existing limitations. Right now we rely almost exclusively on stellar and solar occultations and single platform measurements. So those essentially are limb measurements only, limited data acquisition times dependent on the alignment of the sun and the stars, minimal or non-existent night side measurements, and we have performed outer pointing column abundances in the planetary science community, but this involves a lot of complex assumptions about surface as well as atmospheric temperature and pressure. There's growing evidence for the viability of interplanetary CubeSats or smallsats. The first interplanetary CubeSats were Marco 1 and 2 as part of the Mars InSight mission, and they were launched along with InSight, I believe, but they traveled to Mars on their own, and they survived the journey there, and they performed data relay. Once InSight landed, they performed that data relay. They also had some low-resolution cameras, and you can see an image from Marco over here. So we're investigating places in the solar system where this could be applied. So we've looked at Mars, like water vapor, and a little bit of methane potentially as well. A place like Titan, which is a moon of Saturn. We have some occultation measurements from Cassini, a little bit of in situ from the Huygens probe, but little is known about the aerosols on Titan or the variability of methane and how that relates to its methane-ethane cycle on the surface. So existing measurements could be greatly augmented by a paired system with an EM source of known intensity, spectrum, and source difference distance. So ARKSAT 1 is the first student satellite in the state of Arkansas. It's scheduled to launch in early 2021. It'll be the initial flight and operations demonstrations. We have a payload of a high-power LED and an SSIB deorbiting system. We have a follow-on project of ARKSAT 2 that'll have a CubeSat propulsion system tested as well, and further investigations into the use of the DasCube system for planetary measurements. We'd like to thank Arkansas Space Grant Consortium Consortium, NASA F-Score RAD, and NASA F-Score ISS for funding our work, as well as Dr. Chen and Dr. Wilson of Harding University. Thank you. References.